Hello and welcome back. We've got another video for you today. We're doing something with a cylinder. The volume of a cylinder is given by the formula V equals pi r squared h. Find the maximum value of V if r plus h equals 12. Alright, we've got two pieces of information. We've got V equals pi r squared h, and we've got r plus h equals 12. That's not how you write 12. That's better. Good job. Now, we've got two equations here. One of these, we want to maximize. We want to maximize this happy little fella over here. How do we do it? Well, we want to use this one. The problem with this red equation over here, we can't derive this right now because we've got two variables. We've got the r and the h. That's no good. If you want to derive, at least at this level that the question's set for, you only want to derive with one variable. The pi, of course, is just a constant. It's 3.141, blah, 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 blah. So we want to use this blue equation, r plus h equals 12. This one we can rearrange and sub into the v equation, and we'll get an equation with one variable. So we've got a choice here. We could make h on its own. We could make h equals 12 minus r, or we could get r on its own. So r equals 12 minus h. It looks like there's no difference between these, and it doesn't matter which one we sub in. So for this, I'd like to try both and just see which one is better to do, if there is a better. So let's try the first one, h. V equals pi r squared, and instead of h, whenever I substitute in a value, I like to use brackets. Helps me keep track of any negative signs. That doesn't look too bad. Let's expand that. Pi r squared times 12. Oh, I need space for a 12 at the front. Let me just go back in time. 12 pi r squared minus pi r cubed. Not too bad. That seems easy to derive. I've got one variable, I've got my r. Let's try the r. Let's sub that in. I'll do that over here. V equals pi, and instead of r, 12 minus h in brackets squared times h. Oh, I've got to expand. All right, no, let's do this. I said I was going to do it. I'll do it. So, whenever I'm expanding these, what do I like to do? I like to write each bracket separately. That way I don't forget to apply FOIL correctly. So 12 times 12, 144, minus 12h, minus 12h plus h squared times h. That's going to be pi, open bracket. Let's put this in order. H squared minus 24h, just gathering up those two negative 12h's plus 144 times h, and we can fully expand the brackets. We'll have pi h cubed minus 24 pi h squared plus 144 pi h. Well, let's just compare. We've got this, or we have this. It's a tough choice. It's a tough choice, but personally, I think this one over here is a little bit easier to do. But how do you know? How do you know before you substitute which one is easier? Well, let's have a look. We've got r squared. That's what led to this big expansion of the brackets to fully simplify and expand. That helps us derive it. Here we have h. Just sub in a single value. It's not being squared. It's just h. That's quite a simple expansion. So if you ever do need to sub in, make sure you're looking at the equation that you need to substitute into and figure out which one's the easiest variable to do. So we'll just continue from this point over here. We want to maximize v. So if we see the word maximum, maybe minimum, we want to derive. We couldn't derive before because we had two variables. Now though, we've just got the r, which is quite nice. Let's derive this. So this is 24 pi r minus 3 pi r squared. Lovely. But this is the derivative. How does that help us if we want to maximize something? Well, for a maximum or a minimum, we know that the gradient will equal 0 at that point, or the derivative will equal 0. So if we say let dv equals 0, we can say that 0 equals 24 pi r minus 3 pi r squared. We can rearrange this, we can factorize it even. Take a 3 and a pi and an r out, and I'll be left with 8 minus r. Lovely. Now we can apply the null factor law at this point. Null factor law, because we've got something times something else. So 3 pi r times 8 minus r. So if it equals 0, that means either this first term, this bit here, has to equal 0, or this has to equal 0. So we can say that 0 equals 3 pi r. The 3 and the pi are constants. R is the only variable. That means r has to equal 0. And then we've got another option. Or we've got 0 equals 8 minus r, which gives us r equals 8. Both of these options would lead to the derivative, dvdr equaling 0. But r equals 0, the radius equaling 0, that doesn't help. And also that wouldn't give a maximum value. If a cylinder had a radius of 0, the volume would be 0. So that's kind of useless. So r equals 8, that's what we want to kind of look at. But for the sake of completeness, let's actually look at all of these values. So let's make a gradient table. All we know is that these represent a place where the derivative equals 0, but we are looking specifically for a maximum. So if we say, let's make a gradient table. We've got r, the derivative, and the slope. So if you think of the gradient at a specific r value, so we know 0, and we know 8. We know those. We know the derivative, dvdr, is 0 at those points, which means the slope is flat. So let's pick some values on either side of 0 and 8. Let's make it -1, 1, and 9. I could have chosen 7 here. It doesn't really matter as long as you choose a value between 0 and 8. Now, if the r value was -1, what will happen? Will my derivative be positive or negative? So you can sub in -1, what will happen? So this first term will become negative, this term here is positive, we'll have a negative times a positive, that is going to be negative. That means our slope is going down. If we sub in 1 to this equation here, this will be positive, this will be positive. So our gradient here, or our derivative, is positive, which means the slope, or the gradient, is going up. Now we sub in 9, what happens? We'll get a positive value here. This term here will become negative. 8 minus 9 is -1. So a positive times a negative, that is a negative. So we have two stationary points. We've got two places where the derivative is 0, r equals 0, and r equals 8. If we look around that point here, r equals 0, that's a min. The volume would be the smallest possible. That makes sense. The radius is 0, the volume would be 0. But over here, r equals 8. This represents a max. We can see that if we think about that as a graph, visually it would look like this. So the slope there, or the gradient, or the derivative is 0, and you can see the gradient is positive before that point, and after that point it's negative. So we've got r equals 8 is the maximum. Fantastic. We can now find the maximum value of v. So remember, v equals, what does v equal? V equals this equation over here. We could use our original equation, v equals pi r squared h, but we've just found r. This question doesn't ask us to find r and h, it only wants the maximum value. So you can ignore h for this one. So let's write the equation again. 12 pi r squared minus pi r cubed. Let's sub in 8. 12 pi 8 squared minus pi 8 cubed. Remember, subbing in, let's use brackets. Saves us some trouble, especially when working with negatives. 12 times 64 Who knows what that is? Is anyone good at maths here? Oh, me? Oh, wait, hold on. Let me work this out. 12 times 64 pi minus 8 times 8. What's that? Uh, that's 64 times 8 pi. Maybe I can factorize this and simplify it a little bit. So this will equal, I can take a 64 pi out, and then I'll be left with 12 minus 8. Hey, this works. 64 pi times 4, this will be 256 pi. But remember, we are doing a volume, and it doesn't say what units it is in, but we still need to represent it as a unit somehow. Obviously, if you got to this point here, you could state an answer with decimal values if you just put this in the calculator. The problem is that's not exact. So by leaving the pi there, this value is exact. It is exactly 256 pi units cubed. And that is it. That's the video. We found the maximum value. We've checked by using our gradient table down here. We've checked r equals 8. That is when the volume will be a maximum. And we've done that using derivatives. So this is a optimization problem where you're given two equations. The red one, you need to find the maximum of. The blue one, you need to rearrange and sub into the red one. We had two options. We could either sub in R or we could sub in H. You can see subbing in H. Sorry, subbing in R. Bit of a bigger process. Sub in H because H is just this single value on its own. It's very nice to use. And derive, let it equal 0. Solve, check which one is actually the maximum. Check the nature of your stationary point. You could use a gradient table. You might know other techniques. Whatever is fine. But you still need to check which one you need to use, 0 or 8. Once we've got it, we just sub it back into our volume equation. We could have used our original equation, but we don't have H. So we use the volume equation that has just R in it, and then we solve. And remember, exact units if possible. Alrighty, that's all we got time for. Thanks for joining me, and I'll see you next time.